Yep, get ready for a session that promises to unlock the secrets of innovation. With over 60 patents to his credit and extensive experience in the semiconductor industry, our next speaker is set to share his expertise titled Chips Making Chips: How Virtualization, Digital Twins, and Machine Learning are Accelerating the Spiral of Innovation. Brace yourselves for an inspiring exploration of cutting-edge technologies that are driving us into the future. Your applause, please, to help me welcome Dr. David Freed, Corporate Vice President at Lam Research. Applause, please. David. Thank you so much.
All right, thank you very much. Hopefully everybody had a big lunch and a few glasses of wine, and I will try to keep you awake now. Before we start, I would like to thank the organizers of this event and Critical Manufacturing for inviting me to speak here. It was a tough decision to come spend a few days in Porto in September. It was very difficult. Thank you. But I do have to apologize, Francisco, I'm sorry, I will not be talking about our MES deployment with Critical Manufacturing. Hopefully, I'm transparent enough that you'll see that chips making chips, our end vision of all this, is really built on the foundation of data, of MES, and of transition to Industry 4.0. But first, a word from our sponsors. Just to introduce Lam Research, actually, show of hands, who knows Lam Research and what we do? Okay, not bad. We are a leader in semiconductor wafer fabrication equipment. We have been for 40 years. Our primary equipment markets are etch and strip, deposition, and clean, but obviously also all the support and services that go along with that. That's really what's made us a leader in this industry since 1980, so more than 40 years. We are a global R&D entity, so we have labs and facilities around the world, manufacturing and customer support around the world at all of our customers. In total, we're about 18,000 or a little bit more, almost 19,000 employees now. Now, this is what got us here. This is what made us a leader in the industry. But I typically think about the future and what's coming up. And if you look at this chart, humans have been around for, give or take, 4 million years, and everything we know about happened in the last 150 years. Okay, the pace of innovation is accelerating at record levels. It's going faster and faster. It's a nonlinear acceleration. So whatever we expect in the future, it's coming much faster than anybody planned for. The reason we've become an industry leader in this field and what we plan to continue leading in is because we take on our customers' grand challenges in the industry. So our customers are primarily the fabs, the foundries, the memory manufacturers around the world. And these 4 grand challenges really reflect their challenges that we have taken on as our challenges. So in the semiconductor fabrication business, our customers are demanding atomic scale precision on each of our processes. Obviously, as the complexity has increased, the expense and the cost of these equipment and processes has also increased. So this is a challenge to the sustainability of the entire industry, is the affordability. We are now confronted with additional sustainability challenges as our industry is actually sort of at the forefront of producing some of the most harmful greenhouse gases in the world and consuming massive amounts of energy. And finally, again, because of complexity of the process, affordability of the scaling, and the sustainability challenges, it threatens our ability to deliver these technologies at a pace that the marketplace demands. So we have to constantly be aware and improving, reducing our time to solution, or improving our speed to solution. So now I'd like to take everybody in here through a bit of a time warp. This is the best graphic we could come up with for a time warp. We're going to go forward to 2030. It's not a huge time warp. We're already jet lagged anyway. We go 7 years forward to 2030. And this is really what we see as the era of smart tools and the smart fab. So what does this look like? Smart tools are ubiquitous everywhere in the lab. Tools are maintaining themselves, operating themselves, dispatching to themselves. And as a result of these smart tools, Industry 4.0, and innovation, output of these fabs has achieved unprecedented levels. There's almost zero waste from fabs now in 2030 since we've deployed all these technologies and integrated all of them. And the question is, how did we get there? So sitting here in 2030, it's wonderful. We have record productivity and record yields. Looking backwards to figure out how we got there is really important. Now, I'm going to talk about a few categories of innovation that we have started to deploy, started to implement, but will continue to mature and evolve through till 2030. So I'm going to start with something that we call equipment intelligence. AI is a bit of a buzzword. Inside Lam, we talk about equipment intelligence and how much intelligence we can embed in our products and our services. This is really the transformation of volume production for our customers. So we have to start by defining intelligence, okay? And at Lam, we use Max Tegmark's definition of intelligence, and that is the ability to achieve complex goals. And I assure you, what we're trying to do at Lam Research is a complex goal, as I was discussing before. And so we think about what is intelligence to get there, to grow and to develop that ability to achieve those complex goals. This is actually a photo of my daughters. It's a bit of an old photo. I won't tell anybody how old, but it's an old photo of my daughters, and I'd like to think about the neural nets going on in their brains as they grew up and developed. And as they developed intelligence in a human, what they gained through their maturation was self-awareness, self-maintenance, self-adaptation. Now that they're significantly older than that photo, maybe they're a bit too self-aware, but they've developed those capabilities to become much more intelligent beings. We apply the same 3 attributes of intelligence to our equipment as we develop for the future. So I'd like to step into each of these and define what I mean. So self-awareness is the first one, and this is relatively simple. Self-aware tools, they know what parts are in them. They know about themselves. They know the inside and the properties of those parts and the history of those parts. And this is really absolutely critical for everything we're going to build onto there. A tool can't maintain itself if it doesn't know what parts it has. It doesn't know the vintage and the history and the state. So this is a relatively simple first layer, understanding oneself. The challenges here, and there are significant challenges, is really developing an all-digital supply chain. It's one thing for us to have our designs at the equipment level be all digital and be able to source through that data at our level, but our supply chain, creating our equipment, is many, many levels deep. And if a sub-supplier does not have a digital design system and digital inventory system, that has the potential to cascade and break the entire all-digital supply chain at the equipment level, at the product level. Obviously, being able to transfer data end-to-end and point-to-point within the system, but also within the fab, is critical to having self-awareness. This is beginning to evolve into standards, but we're really not there yet. And so we're developing our own standards inside each and every one of our own companies. And obviously the IP, the concern about IP and knowing the parts and the system inside and out is really critical to gating self-awareness. Now self-maintenance, this is really important. So this is a look inside one of our etch chambers. I don't have a pointer, but I'll point with my arms. Often these chambers need to be opened and replace parts. We make etch equipment. It eats itself. It's a wonderful business model. And so quite often, historically, we would open the chamber to replace those consumable parts, clean the chamber, close it, and return it to manufacturing. That process of opening the chamber, cleaning it, was a massive availability hit for our customers. Hours of downtime on chambers. And so what we've started to do is now that white part is the edge ring. It's a consumable edge ring around the wafer. That gets replaced in that chamber automatically by the tool itself. We do not have to open the chamber anymore to place that edge ring. And in fact, that chamber, the Keough conductor etch chamber, can run for the effect of a full year without being opened in a manufacturing environment because of consumable replacements that way. That said, those parts, that part and others, need to be placed with a precision of 50 microns or less. That's really extremely challenging, and so we've also developed a system, and you see it here, laying on the center of the chuck is our Lam automatic positioning system. So that's a system that gets loaded by the tool onto the wafer chuck and measures the alignment of all the consumable parts that are installed. Okay, so this self-maintenance, there's a ton of innovation here, not only from parts, from system integration, but also all the data flow and communication that the automated positioning system needs to use to guarantee correct placement of those consumable parts. Now, what gates self-maintenance? What's the growth process like my daughter's to get to full maturity here? I just talked about some of the challenges in tool architecture. So we have to design our system to maintain itself. But also beyond that, there's a significant impact to fab infrastructure. Those parts, those replaceable parts, need to be delivered to the tool for those operations. We saw earlier some images of robotics in the fab, and that's expediting that integration with the fab. But we can't just design these tools self-maintaining on our own. We talk about fab tool co-design. So we design the tool to do things that integrate with processes that our customers have to implement in their fab as well. And again, this is starting to evolve into standards, but it's very early days here. And that final piece, self-adaptive. And so we think about self-adaptation as the ability to modify your operation based on circumstances or current state of the operation. One great example of this is we have an etch application, and it's a very challenging etch application. That's a deep etch, and there's no stop layer. So we have to etch to a certain depth, know we're at that depth, and stop the etch. It's very, very difficult, especially because wafers are arriving at that etch step with all sorts of different variations from previous steps. So what we've done is we've implemented what we call LSR, which is Lam spectral reflectometer. We have a white light reflectometer in our etch chambers, observing the wafer evolving through the etch process. So we get broadband reflectivity through time during the etch. And we've taken that data, which is multidimensional time series data, we've used that to train machine learning algorithms, and we've implemented those algorithms in our etch tool to stop the plasma, to extinguish the plasma in the reactive ion etch when we've reached the appropriate etch depth. Okay? What we find once we've implemented this is a 50% reduction in the etch depth variation at our customer fabs. 50% variation reduction is worth many points of yield to our memory customers specifically. Okay? And again, this is a complex innovation and adaptation that's born on sensors, data integration, but then machine learning and implementation of a control mechanism based on that machine learning. So we put these things together, self-aware, self-maintained, self-adaptive. Now what gates adaptability? The data flow is one of the more challenging ones in adaptability. The example I showed is literally a real-time adaptation. Each wafer is endpointed differently based on that reflectometer signal. So getting that data to flow from the sensor to the control circuit to the equipment controls is really, really challenging, getting that through the modules. The algorithms to optimize the machine learning are challenging. And again, getting to standards and not crossing IP barriers is really key here. One thing I'll mention here about adaptability, this is a system that's entirely built into a Lam etch chamber. So we've made our system adaptive based on what we can observe. But if we're going to extend that adaptability to multiple machines across sectors in the fab, this is going to require additional layers of data flow and data communication in the factory. Okay, so wrapping up the equipment intelligence section, this is more than just a smart tool. This is really a new industry mindset of self-aware, self-maintained, self-adaptive, and the entire ecosystem really needs to respond. So I started by talking about the all-digital supply chain, but getting the data to flow correctly and transfer through all these different modules, being able to co-design equipment and the factory all at once, and then implement big data algorithms in the system is really key here. Collaboration and the response of the industry to collaborate is going to be required to really evolve this to that vision of 2030 through the time warp. So now I'm going to transition a little bit to what we call semiverse solutions. I heard a mention of the metaverse earlier, but we talk about the semiverse. It's really the coming together of virtual and physical in the semiconductor ecosystem. We, as earlier speakers were talking about, we've heavily invested in digital twins and the digital thread for our equipment in our customer factories. The digital twin is really the virtual representation of the asset, and the digital thread sort of through its lifetime, and all the associated data and the processes that go on that tool. With the digital twin, once we have an all virtual representation of our equipment, we can implement that in many different ways. One example here is what we call the virtual build. Let me see if I can start this. And so what you see here is just a virtual build and a virtual mock-up of one of our chambers, the top end of one of our chamber, and actually a platform system. And we've implemented this in our manufacturing operation, our pilot manufacturing. So we're identifying pinch points, part overlaps, assembly sequence issues, long before we've ever cut metal. Okay, so this has substantially reduced our pilot manufacturing phase, so we can transfer into volume manufacturing without all those problems. So that's one very easy and obvious example of the implementation of digital twin. Now, the digital twin and digital thread has also enabled other applications, significant other applications, like virtual reality and augmented reality. Now, we have invested pretty heavily in VR for training and AR for maintenance operations. And so you see here, this is a new service engineer being trained on how to service a piece of our equipment, sitting in our VR lab, able to select tools and perform complex maintenance operations in virtual reality before ever being sent out into the field. Now, a really interesting aspect of this happened at the beginning of COVID. I was explaining those complex maintenance operations where our service engineers would have to open chambers and replace parts at the customer. About March 16th of 2020, when travel ended completely, we couldn't send service engineers into our customer fabs. And so all of those service operations would have just ended completely, if not for our AR-assisted maintenance operations. So we couldn't send service engineers, but we could send glasses. And we ended up shipping glasses to many of our customers and enabling their engineers with our assistance to go do maintenance and service operations in the fab, eliminating our travel. And this really, to be honest, has saved a huge amount of business during COVID to enable that. Again, this is built on the back of full digital representation of the equipment, and then all of the data and all the implementation details to enable that type of complex maintenance and service. The final topic I want to get to here is virtual process development. Now, I talked earlier about how equipment intelligence has really transformed production and high-volume manufacturing. Virtual process development is all about transforming R&D, research and development, into our equipment and the processes that go on our equipment. One of the interesting complexities of making process equipment in this industry is we can't just sell the equipment to our customers. We have to sell the equipment with the recipe that meets their specs. So I always talk about going to the appliance store and buying an oven. They don't sell you the recipe for brownies. You just buy the oven. In our business, it's very different. We sell the recipe as well. Okay, so just without being too boring, we make the process that makes the chips. So if you think about a 300 millimeter wafer, on there's many chips. On those chips are many devices. On those devices are many layers, many complex structures. Just because you can design the chip, so many of the fabless companies or the IDMs, they design, doesn't mean you can fabricate it properly and yield it. Many people are familiar with Moore's Law. I'll tell you what, I said it doesn't mean you can build it. In Moore's Law, we talk about this feature size over time descending on a logarithmic scale. And so we're to the point where our feature sizes are below 10 nanometers now as we progress into the 2020s. We have another law that is referred to as Lamb's Law. And as we've scaled the feature size and the complexity of technology dimensions, the number of possible recipe and recipe combinations on a given tool or in the fab has scaled exponentially the other direction. Okay? In one of our more complex, an etch tool, a conductor etch tool right now, the number of possible recipes it can run is on the order of 10 to the 23rd. And we're asking a process engineer to find effectively one process that works for the customer and hits the customer spec in 10 to the 23rd options. So that's not a needle in a haystack, that's a needle in a universe of hay, right? It's nearly impossible. And this is really one of the key technical challenges in development and putting these processes into early manufacturing. So with that scale of a problem, you would think we have all sorts of brilliant and innovative ways to do this development. Actually, largely we don't. We still do process development the old way. Okay? A customer gives us a spec, and the spec is usually in terms of dimensions on a critical structure on the wafer. Often those specs, I will say today, those specs have expanded. We need to hit 50 or 60 different dimensional specifications on a given wafer to win an application. We have human process engineers that make a process hypothesis. They take wafers into the fab. They often break those wafers up into small pieces to conserve material. And they begin iterating through process options and process parameter choices. They measure, they analyze, they repeat. Okay, this is an incredibly expensive and time-consuming process involving many humans and many very expensive resources. Once we finally hit the spec, we deliver the process to the customer. It often behaves differently in the customer fab, and we restart this process. So this is the old Edisonian method for experimenting. It is still largely the backbone of process engineering in the industry. On the design side, I mentioned it before, they've gone to incredible amounts of automation in chip design. So the question we asked ourselves is, why can't we design a process the same way they design a chip, with automation and machine learning and advanced technology? And so we asked those questions. Why can't we do it? Why can't we just use physics? Do we understand all the physics in our reactor? Do we understand the process that we're actually building around? The answer is, in many cases, not really. There's too many unknowns, and the processes, we predominantly focus on reactive ion processes in plasma reactors. There's too much complex physics to accurately predict at a high resolution these recipes, and to do it fast enough for our customers. And we look at the other end of the spectrum, we say, well, we have data, we have all the data from the lab, why don't we just use data? And the answer is we're actually in a small data world where we can't apply a lot of these big data techniques. As I said before, the process engineer is trying to choose one recipe within 10 to the 23rd options. The dimensionality there is massive. The number of data points we have will never approximate 10 to the 23rd on a given process operation. So we'll never have enough data to do this purely with data. What we found is that we put these two together. We meet somewhere in the middle with physics and with data, and we're ending up successful. So I want to talk about a very specific example of this now. So this is a cross-sectional SEM micrograph of Samsung 92-layer 3D NAND. And in that blue box, you can see what we call the memory hole. This is an incredibly high aspect ratio etch. It's an aspect ratio of about 100 to 1. Meaning it's about 100 times deeper than it is wide. It's a circular hole. Okay? This is one of the most challenging etch applications in the industry. This is also probably our primary focus in our etch division is etching that hole, etching it perfectly, and we etch about 1 trillion of them on every wafer. Okay, so that's one of the key applications in our industry. we said, hey, let's play a game. We developed a game to play. This is a dangerous little social experiment we did within the company. We made a game to benchmark different human or AI approaches to developing that etch recipe, that channel hole etch in the 92-layer 3D NAND. So to create that game, we built a virtual environment for high aspect ratio etch. And what does that mean? What is a virtual environment? This is essentially the digital twin of our process. All right, we started by defining an incoming wafer, an incoming structure on the wafer. We then created a virtual representation of the plasma reactor with all of its input process parameters and all of the behaviors that that reactor delivers from those process parameters. We then apply those behaviors to the incoming structure, we predict the outcoming structure, and we iterate until we meet the spec. So we've created a full virtual environment, and now we can test what's the best way to solve this problem. Okay, so no presentation is good without some complex data charts. So I'm going to start over here. These plots are very interesting. What they are is the y-axis is essentially distance to hitting the spec. So when the process engineer starts the first runs, they're nowhere near the specification. As they begin iterating, they progress to the bottom of the chart. They've hit the customer spec, and we created a cost target or a cost structure. So every simulation in this virtual game would cost a certain amount, just like our wafers would cost in the lab. And what we found here, this first chart, is that our best senior process engineers could get this problem done at about $105,000 of our artificial virtual cost. What you see here is our junior process engineers took significantly longer. Now, all of these process engineers, the shape of that curve is quite characteristic. What it shows is at the very beginning, they were able to make great, huge strides of progress. And then at the end, it took them a very, very long time to get all the way to the spec. It's a very characteristic curve. Okay? Now, interestingly enough, these are non-process engineers. We released the game to our human resources department, to our corporate communications department, and to our IT department. And what we found is very few of our HR, corp comms, or IT people could solve this process problem. So there's some technique and some technology to it. And the final chart here is we took an AI algorithm with no training. We threw the problem at that. And what it shows, it took $720,000 to solve the problem. And this basically shows that without any internal or initial intuition, without any training, the algorithm is much worse than our experienced process engineers. For those skilled in machine learning and AI, this should come as no surprise, but it's quite interesting that the computer will not replace the process engineer right now, for sure. Okay, what I said previously is that the shape of this curve, it really is in two phases. The initial is what we call rough tuning. That's where the process engineer and the human provides a lot of value, a lot of experiential knowledge, is able to baseline from previous work, and can make 80 or more % progress to the target very quickly. That fine-tuning, getting to the bottom and hitting the target, is very, very expensive, takes a long time, and actually is very, very frustrating for our engineers. That's when many of our process engineers decide they want different careers. In our dielectric etch group, I had the GM tell me, I have engineers that are 1 week away from the spec for 18 months. That's that part of the process, and so that's really challenging here. What we see is usually the humans, when a human tries to do that tuning, they're doing univariate process recipe skews, changing one process at a time in a granular way. What we decided to do was experiment with letting the human do the first iteration and then handing the process off very quickly to the algorithm. And what we found is if we transfer very, very early in that process, when the human has just made initial progress, hand it to the algorithm, about 42% of the time the algorithm beats the human to the finish line. Okay, not bad, but not great. If we hand off a little further down the curve, we were able to get 99% of the time the computer would beat the human to the finish line. And it just shows this particular set of algorithms were exceptionally well optimized for highly multivariate, highly dimensional optimization, what computers are good for, right? And so this was a great set of findings and really has impacted the way we do process engineering at Lam right now, is we've coupled humans and engineers together to have us both doing what we're best at. We've even studied sort of when is the optimal point in this process to transition from human intuition and innovation to AI and machine learning. And so this is a type of chart we look at that looks at, how far down the curve are you trading off versus how many of your runs are beating the human home. So this is a really important set of analysis that's changed the way we do process engineering now. So I think the take-home message from a lot of this is AI is not necessarily going to replace humans in any of these processes, but if we embrace the best capabilities of the engineers, of the talent, of the intuition, with the best capabilities of machine learning and AI, we actually get a much better result, specifically in some of these repetitive and tedious tasks like that final optimization. Now, I will say this was a pretty broad study, and so we wrote up our findings, and actually this has been published in Nature. And so this is the citation. If anybody wants it to read the full paper, it's fairly exhaustive in this human-machine collaboration. But we have begun implementing these techniques, and we have dramatically accelerated our time to solution in process engineering as a result. Now, I talked a little bit about the cost structure there. If we were to map that to a real cost structure, and here's the business impetus for this. Real experiments cost about $1,000 and take a half a day. A simulated experiment, by comparison, costs about 11 cents. And that's mostly compute cost. Takes about 8 minutes. Now, if we have enough data, enough simulation that we can create emulation, the next step in our progression, it's nearly free and nearly instantaneous. And so you can see how quickly we can accelerate time to solution as we progress from the physical full experimental path through to an ML and AI embedded virtual process development. So I just want to wrap up with a couple of points. So again, in R&D, we're in a little data problem, right? We're never going to have enough data to do process engineering with data alone, so we have to maximally leverage the information that we have and our real experiments and our human expertise. One thing we found here is we created this virtual environment. It was as good as we could make it. It doesn't have to be perfect. These models, as Box once said, all models are wrong, some of them are useful. The more we make these models representative and somewhat predictive, they become wildly useful very early on. Now, this virtual environment, I talked mostly about it in terms of process engineering technology, but we've started to implement this in terms of training. The virtual environment is a wonderful way to train new process engineers without the cost and expense of a lab, but also to train engineers in locations where they would never have access to the lab. I talked in depth about how we've enabled aggressive speed to solution in our process engineering through this and reduced our costs. It's not a panacea, it's not perfect, but I think it's pretty darn close. So in conclusion, I think it's really exciting that we see ourselves really in the middle of this virtual and accelerating spiral of innovation. Obviously, we have our electronics, we're able to make the models, we develop algorithms to develop recipes that go on equipment that create new processes in the fab to create the next generation of chips that go into the servers and compute environment that we're going to use to continue optimizing in the future. This is a very virtuous cycle, and it's spiraled us to greater and greater points in our circle of innovation. With that, I'll say thank you very much. Close out.
Thank you, David. Thank you so much. Thanks. An applause for these gentlemen. Thank you.